All right, I think we can get started. Okay. Welcome everyone to the second part of the remote sensing workshop with LP DAAC. For those of you who missed the first part of the workshop, my name is Yufang Jin from University of California, Davis. This workshop is jointly hosted by California View, which I'm leading right now as a member of the nationwide America View Consortium, and also by the Informatics and GIS statewide program from UC Division of Agriculture and Natural Resources, led by Professor Maggie Kelly from UC Berkeley, coordinated by Dr. Sean Hogan. Maggie and Hogan both here. And today we are joined by several staff members of LP DAAC, including our speaker today, Erwin Fritz, who is the science coordinator of LP DAAC, and Daniel Garland and Masa Jamie's here as well. So I think with that, Maggie, you want to say a few words before we hand it over to Sean for the housekeeping items?
Sure. I'll just say welcome, everybody. It's a thrill to be with you on this lovely Friday. I know you're all into this stuff like we are, so I'll kick it over to Sean to get us started.
Great, thank you. And I'd like to echo the thank you to LP DAAC for putting on this two-part series. It's been excellent so far. If you weren't here on Tuesday, we have a couple items I'd like to touch on. One, if you have any questions, please put them in the chat. You'll find the chat button down on the bottom, along the bottom of the screen. We have an excellent crew of help from LP DAAC that can field questions in the chat, or wait for a moment, usually right before or after a break, when they can relay those questions to the instructor. So there could be feedback for everybody. The other thing I'd like to mention is that this is being recorded, and I will publish this on our UCANR-IGIS YouTube channel next week, and I will send a link out to everybody. So just know that it's being recorded. And with that, we can turn it over to Aaron and Danielle.
Thank you so much. All right, so this session is going to be a lot more hands-on, and there are a couple must-haves that need to work in order for you to really be involved. And so, first of all, the GitHub usernames and the Earth Data login. Please make sure you have your Earth Data login on you, and then also that you send us your GitHub username. We need the actual username and not the email to get you added to this environment. And so before we kind of dive into the presentation part, I want to share this link. Oh, yeah, it's already in the chat. There's a link to a repository, and that's going to be kind of the thing that we go back to, or at least tracks how we progress through these exercises. And if you have given us your GitHub username already, click this Launch Interactive Notebooks. I'm going to zoom in a bit. And this will kick off the environment that we're going to be working from today. And I want to tell you to do this right now so that if you run into any issues, please reach out to Danielle or Masa and let them know that you're unable to access that, and then we can try to troubleshoot while I'm doing the more presentation part of the demo. And then I'll talk a little bit later about what you're actually doing here when we're logging into this space. Okay, so if you're having trouble accessing this space after clicking login, and then there's a authentication for GitHub, this is where you enter your GitHub username. If you don't get in, please reach out and we'll work through that issue at that time. So presentation portion, I'm going to try to go through this fairly quickly, and this is just really kind of designed to let you know where we're coming from. I mean, not only from a NASA standpoint, but also from LP DAAC. LP DAAC here, we're under a couple umbrellas. The Earth Science Data System Program is a program within Earth Science Division. And we're charged with processing data. We're charged with actively managing that data so that it's continues to be fully open and available to our science communities. We also have a hand in developing capabilities, services, systems that allow you to interact with that data to really advance your science. And then a part that we're kind of more involved in now, more now than ever really, is engaging with our Earth science community. So doing events like this, doing hackathons, creating tutorials from use cases that maybe our users will send in or that we kind of harvest from literature. All of this is kind of to make science easier on you. And whether that comes in the form of creating tutorials or giving you a work environment to give you a space to work with new cloud capabilities, that's what we're trying to do and trying to push. And so far, I think it's been working out pretty well. Open data to fuel open science. There's a large push to keep things open, keep data, keep services, tools, utilities, all you name it, open, available, and work kind of in a collaborative mode going forward. So there's a number of activities and benefits that go along with that, but I'm going to kind of leave it at that and move into the ESDIS portion. So this is another umbrella that we fall under. We are the largest largest data repository of earth science in the world. And here are a few statistics, I guess, about 441.8 petabytes of accessible earth science data. It's probably much more than that now that it's 2002, but I mean, that number is expected to explode in the next couple of years with the launch of some newer missions, NISAR and SWAT, in addition to some of the other Earth Observatory platforms that are planned in the coming 5 to 10 years. So this number is only going to grow. The volume, the veracity of these data products are pushing us further into that big data era. LP DAAC, we're one of 12 DAACs that are on this journey, this migration to the cloud journey. And so this is really an LP DAAC-centric viewpoint, but a lot of the examples that you show can be leveraged with other DAACs with some modifications, of course, and we're working to kind of create a system or an ecosystem of resources that highlight all of the DAACs together, and that's kind of a work in process right now. Again, the era of big data, we're definitely within it, and kind of one of the solutions, I guess, to this is moving to the cloud. Working with big data on-prem, for the most part, is not very feasible if you're an individual working with data. If you have the capacity to purchase large machines to do that data processing, it's can be very expensive. And moving to the cloud is really kind of an obvious solution, I guess, to many of us. But there is a lot of convincing, I guess, to go along with that. And so that's why we're holding these kind of outreach events, workshops, and hackathons to show people how to leverage our data in the cloud and hopefully bring them into that space. So a couple, I'll be kind of treating you as a 101 course here, just with some cloud terminologies, because it gets very easy to throw around acronyms and get lost in those. And so when I'm talking about the NASA cloud, I'm talking Earth Data Cloud, and that's how I'll refer to it as, is the NASA Earth Data Cloud. And what that actually is just the cloud space in Amazon Web Services, or AWS. And specifically, we're referring to a specific zone in AWS, the US West 2 zone. And this is where all of our data, all of our services are being archived and produced. And so NASA has this thing where you cannot, if you're working in the cloud, you you cannot pull the data across the zone boundary without an egress cost. And so to keep that data free, keep it accessible to our users, working within the cloud or working within that specific US West 2 region is required. AWS data storage, you'll hear S3. Those are just the buckets, or the S3 buckets where data is stored. Will require S3 access keys at some point. These are needed to work with AWS to show that system that you are a valid user of this data. And we'll kind of talk about that later in one of the hands-on activities. There's a term called EC2, or Elastic Cloud Compute. These are where all the processing, the storage, networking, operating systems are kind of being implemented. This is the system that you're running your analysis in. There are a number of costs to consider if you're kind of going at this alone and setting up your own system, right? There's the compute costs that are involved with doing processing, storing data. There's a cost to that. So if you're using NASA data, which is openly available to you, but you're storing off intermediate products, there's a cost to those storage requirements. And then there's egress costs. So that's the egress. When you hear egress, it's you're pulling data out of the region, or you're pulling data out of the cloud. And there's a cost associated with that. In most cases, NASA has it set up so that you can download data from the cloud. But if you're doing this thing called direct S3 access, you're not able to pull that data out of the cloud. So data in general for NASA is still freely available. You could still download that. What cloud offers us is a different way, a different paradigm of working with that data. And hopefully it's more of a fit for big data analysis. One of the aspects of the cloud is the ability to create, or one of the strengths of the cloud is it allows us to really kind of work with data in a different way, especially if it's in this thing called the cloud optimized format. There's a couple different cloud optimized formats that are available right now. I have one listed, ZAR, here. There's another one called a cloud optimized Geotiff, which is more or less a Geotiff in all forms, but it's kind of organized separately or differently so that you can access that in chunks, and we'll talk about that later. When we are talking about cloud optimized formats, we're really kind of talking about internal chunking of those files so that you don't need to read in an entire file each time you're working with it. You're actually identifying, or the utilities that you're using are identifying spaces within that file and pulling out those little chunks rather than reading an entire file. And so when I'm talking about cloud optimized formats, that's kind of what I'm referring to, are data formats, data files that are chunked and that can be read in an optimal way. So I've mentioned paradigm shift, and this is, getting to be almost outdated, where on the top we have kind of a historical view of working with data, where you access a DAAC data archive that maybe has its own API, which is kind of different than another DAAC API. It's a very siloed way of working with data versus kind of this in-place way of working with data where all the data is kind of stored in a common location. All the services are in a common location. We can have these interactive web environments that are deployed in the cloud, and you can use these common kind of packages or utilities that have been developed to work within those interactive web browsers. And they all are kind of loosely coupled so that, I can have a data structure like Xarray in this case that speaks to DAAC for my parallel computing. It also speaks with HoloViews for my visualization activities. And so these types of ecosystems are maturing and they're very useful, specifically from a programmatic standpoint if you're doing programming. But that's kind of the intent, is to kind of keep everything within the cloud and only have to pull out your end results. You don't want to be pulling a lot of data and moving a lot of data across the cloud. This just kind of highlights that. I mean, we're actually moving not only data, services as well, tools as well, to the cloud. So we have ways of searching for data, like Earth Data Search Client. That's a phenomenal tool for identifying anything that's in the cloud right now, and allows you to get those download links like Danielle showed last time, and really kind of use those. Virtual directories is still kind of a work in progress. It's a way of kind of displaying what's available at our archive, whether it's in the cloud or not, in kind of that normal directory view, hierarchical directory view of those data. There's efforts to create this Harmony API. Actually, it has been created and it's being built on. This is a way to kind of consistently search across the archives and gives you transformative services against those data that it's kind of connected to, so that you for NASA assets, Harmony API would give you that single consistent access point to these data once it's all kind of developed out. Still pretty early on in that the maturity of that API at this time. Programmatically, if you're searching for data, you're probably going to want to use the CMR API for NASA assets, and the documentation, I believe, is at that link. But this is just an API that you can use to search against the CMR, or the Common Metadata Repository. It's kind of the master repository for all NASA assets, and the API gives you a way to search against that, and really you can narrow down your search, your temporal area, your specific kind of fields that you're interested in, whether it's cloud cover or a certain quality of that file. And so it's very powerful, very robust. OpenDAP is a system that's been stood up in the cloud as well, and it is a way of subsetting data without having to download the data. And so that's another capability that's on-prem right now. It's also in the cloud right now. And that's also kind of gaining more data sets that are connected to it. And then we get to the in-cloud data access. So we have a number of ways of doing this, or a couple ways. The Harmony API does this for you. But we have a number of resources that show you how to do what we call direct S3 access of these data. And it requires a handful of requirements to do that. And we'll show those in the upcoming tutorials. And then there's some just interesting ways or libraries that are being developed that can more or less treat a non-optimized format, or non-cloud optimized format, like a netcdf4 file, as a cloud optimized format. And so just some interesting stuff there. And if you're interested in that, please reach out. We can talk a little bit more. It's very kind of, I don't know if cutting edge is the right term, but it's very new stuff. So here's our cloud ecosystem right now, and this is a very kind of programmer view of the cloud and the relationship with the user. We have about 3 kind of data access models or ways of working with the cloud. So of course, we're working with AWS Cloud. We're working within US West 2. All of our services, all of our data are co-located in the cloud. So you have access to those if you're working in the cloud. One of the ways to work with data, work with services, is as you have always worked with data from a completely local server that's not in the cloud. And so you could still access services, you could still download data. These are still free, but it's a kind of a non-optimized way of working with the data as it is stored right now. Another way is to have which one is this one? User. So this is a user can go in and set up an environment from scratch. They can go in, they can say I AWS account, I want to install this operating system, I want to deploy these Jupyter Lab instance and bring in the recipes. Again, the data is free, the services are free, and so the only charge there at that point is you as a user standing up your own kind of cloud environment. You're paying for those compute cycles, you're paying for any storage of the data that you're producing, and then also you're paying if you're pulling data out of the cloud. Or you can have those resources, you can basically contract those resources out, use an entity like 2i2c or Coil. These are management systems or companies that manage the deployment of these types of environments in whatever region you want to be. You want to be in US West 2, but they'll deploy a Jupyter Hub instance for you and allow you to add and remove users as you see fit. But basically everything, all of the under the hood things are done for you. And then you just need to worry about adding people and making sure that the environment you're working with has the packages that you need. And then you're off and running. And we'll see this type of environment later on. And maybe you already are seeing it today. So that was a fire hose. I just wanted to kind of get that out of the way so that we understand the context of some of this stuff. Let's get out of this guy. So I'm hoping that some of you have successfully entered into the work environment. I'm going to post this link again. Here's the link we'll be working from again. This is a repository that we set up in our kind of, oh, that's the wrong one. You can use that one too. But so to make things confusing, I apologize there. So that's the unofficial repository. The official repository is this guy. They're the same thing, just one's in my personal GitHub. So if you go into this guy, let's see, that's repository. And really all I want you to do if you're here is click this launch interactive notebook. And if you don't want to follow along or within these notebooks or do the interactive exercise, you can view those static notebooks as well. Those are pre-rendered notebooks that you can just kind of scroll through if you want. So click in that launch interactive notebooks. It's not working for me. I wonder if it's my VPN. So maybe while this works itself out for me, I'll open it up for anybody getting or in the process, I guess, at this time to see if we are having some success deploying this environment or if this is an overall issue that we'll have to tackle. We got working. It's working. So the instructor is the only one who can't get in now. Working, good. Got server options. Just pick the smallest one. All of these notebooks were developed on that small one, and that's all you'll need. One thing to note there is, I mean, if you are managing your own environment, the bigger you go, the more money it costs. But something to realize is that, I mean, cycle, or if you're running an analysis for a shorter amount of time, you could be paying the same as running a long analysis on a smaller machine. All right, give me 1 second. I'm going to jump off VPN and that will disconnect me for a minute. All right. There we go. VPN was not liking me. All right, so hopefully a lot of you got to this GitHub sign in. This is why we need your GitHub. This does require authentication, so that's how we kind of let people in and get working. You probably didn't land on that screen. You should land on a screen like this one.
Hey, Aaron, can you please reshare your screen?
I can. Sorry for the confusion here. There we go. All right. So I have a number of notebooks or repositories that are in here. What I'm hoping is in all of your Jupyter Lab instances, this LPDAAC Cloud Data Access repository. And so if you click into that, that's where we're going to be working from. Everything starts in this folder. First thing we want to do is set up authentication. And so you have an Earth Data login because NASA requires authentication for all data that's downloaded from their DAACs. This isn't needed to view information, view metadata, but if you want to download that Earth Data login needs to be passed in order to do that. And so the way to do this from Python is to create, or at least the best way that I know of, at least right now, is to create a .NET RC file, which contains the machine name of the authentication server, along with your credentials from Earth Data Login. To streamline this, there is a notebook. So if we are in the LPDAAC Cloud Data Access folder, and we go to Notebooks, and we double-click that, and we click this NASA Earth Data Authentication Notebook, the second one down. This should bring up a Jupyter notebook that has some lines of code. So this isn't something that we're going to walk through. This is designed to just run it and forget it. And this will create a file. It will create that netrc file for us. And it will enter the proper credentials in there for us. And then we're basically off and running if everything is successful here. And so what I want you to do is, after opening up this notebook, go to Run, and then do, at the second from the bottom, Run all cells. And what this will do, it will immediately take you to a prompt to enter your Earth Data login username. So that's what we'll do first. Oops. I'll hit enter, and then I'll enter my password. And this is critical. This has to be correct, or else nothing will work. So let's enter. And this will run the rest of the notebook. And what we're looking for in this list command here is a .netrc file that's produced right here. So if this is not in this list of files, please let us know. Another way to inspect that netrc file is to go to File, and then you can open from Path, and then you can type in .netrc and hit Open, and that should open up a text file that has that information in it. Netrc, not CR. Okay, and then if you view that and you have the proper credentials in there, then we're good. But it's a quick way to see if you indeed enter the right username, enter the right password. If you didn't open or enter the right thing, you could change it in that view and then save that file, and we should be good. So please let us know if you were not able to create that netrc file successfully. And let me know if I'm not sharing my screen still. How to check this. Okay, so 1 second, let me. Yep, you just enter your credentials. So, right now we got I'm going to run this again. So if you open up the notebook, I'm going to do a run all cells here from this run. I got to enter my username and then my password. Okay, I'm going to put the wrong one in this time. Run this one. You got an NetRC file. To view that in a text editor, you go to File, go to Open from Path, and then just type in NetRC. And that should open up a text version of that file. And you'll see that there's a machine name here. You don't need to worry about that. What you want to look at is this login. This is your Earth Data username. And your password, this is your Earth Data username or your password. So just make sure those two things are right if you experience any problems. And that's just how you view it from a text editor. And one more time. Repetition. All right. So now we have a file that the rest of our notebooks can use to authenticate us. So we can close out of this notebook. You could save or discard whatever you want to do. We're going to go back to that LP DAAC Cloud Data Access folder. And we'll kind of get into the meat of things. We want to access this notebooks folder again. We're going to go into this topic 1 notebook. All right. So this isn't specifically about LPDAC only. This is to give you an idea of the variety. And it's just the tip of the iceberg of the different ways maybe an S3 bucket can be set up. That impacts the way you access that data. We're dealing with cloud optimized geotiffs in all scenarios in this one, but we're going to be looking at kind of 2 sources and 2 varieties, I guess, within the NASA realm. We're going to be looking at free and open data from AWS or the open data on AWS. We're going to grab a Sentinel file and just see what that's like. These are completely free, completely open, require no authentication. Very low barrier of entry, if any, at all. And then we have NASA assets, which require that authentication. And so we'll show you how to set that up and how that works. And then also something like the Landsat archive from the USGS. That is in the cloud. It's also in US West 2, but it is a requester pays bucket so that you can actually access this data from another region within AWS. But that movement of the data across those region lines will incur a cost, and any request or GET request or what have you will have another charge as well. And so there's if you're out of region, out of US West 2, there is a charge to accessing that Landsat data. And again, very AWS centric. So there is no consideration for any other cloud at this point. And so that's what we're going to do. We're going to import the required packages here. The big ones here are going to be the request library, Rasterio for handling the geospatial data and reading that in. Also, there's some sub modules in there that allow us to pass credentials or pass environmental variables to our requests. So we definitely need to set those up to access data. And then GDAL. GDAL is a foundational element of most, if not all, geospatial software and utilities. It has a few kind of environmental variables that we need to set that allow us to access these data. Okay, so back to that GDAL. There's a number, if you're familiar with GDAL, it has a number of configuration options. And specifically for our purposes here, the configuration options that we want to set is the GDAL disable read dir on open. What this, to my understanding, does is it makes the request focus on a single file that you're specifying. and does not look for like supporting or sidecar files to harvest metadata from and apply on the fly. This just finds that Geotiff file that we're looking for, and it brings it in. If you don't have the set right, you likely get an error that is quite difficult to track down. Another big one that we're using is this cookie file and cookie jar option. What this does is holds on to our kind of cookies when we make a request that requires authentication, so that we're not constantly sending our credentials into the system and it's having to verify and then send back cookies that says, yes, you're okay, user. This will store that information so that it's a much more efficient way of moving your credentials or identifying that you're a valid user. And those are really useful, I guess, for NASA data. But in these first couple of shows, we won't even use them. The cookies one anyway. So getting into the free and open, this is Amazon's Sentinel data. We have a URL to a cloud data asset here. We're going to hit Shift Enter. If you're not familiar with notebooks or Jupyter notebooks, to execute cells, you hit either Shift Enter, which will do execute a cell and then move you to the next cell automatically, or you can do Control Enter, which will just execute that cell and keep you in that space. Next, we'll run this cell here. And did we execute the? Oh, I didn't import my packages. So once again, hitting my Shift Enter, and I can kind of tell that because the cell number was 1 down here when it should have been 2. So now we'll run this cell down here, which is using that rasterio library to pass those credentials or those environmental variables in. It's now reading that URL here and bringing it in and just grabbing some information from that TIFF file. So it's grabbing information about the file itself. It's grabbing some overviews if there are overviews. And then it's going to just do a quick plot. So if you do a Shift Enter on that, you get an immediate printout. Gives us information about the file. It's a Geotiff. It's got unsigned int, no data, some attributes about it, the projection, and the like. We have overview levels here. In this case, we got 4. And just a quick kind of exploratory printout. Moving on to authentication. So we got another one that's in a similar location, but this asset is actually coming from the LP DAAC cloud location. So we'll enter on this, or Shift Enter, and we'll be accessing an HLS S30 tile here. And it's in kind of western Nebraska is where this kind of lies. In this case, we're going to set that cookie file parameter, and that will help us kind of authenticate later on. Yeah, and then kind of bringing in same information. We're connecting to that URL. We're reading it in. We're printing off some file information and some attribute information, printing off the overviews for this. And then there's a couple other variables that we specify that we don't use, but assign them regardless in this case. And so this one takes a little bit more time because I think it's there's an application called the T application, or Thin Egress app, that is distributing the data for us. We're not accessing this data on S3 directly. It's coming through an access mechanism. So again, we get that file information up here, we get some attribute information, chunking sizes, and then also the overview here as well. So we got just a simple, again, printout that we can kind of evaluate a bit. And then Landsat. So Landsat is a requester pays bucket, meaning, again, that you got to pay to access that. And if you're in US West 2, actually that charge does not count. So if you're outside the region, you would have to pay for that. So we're going to establish, this session, which passes information to AWS. And so this is a client for the AWS command line interface. And what it's doing is just saying, this is an AWS user. And then we're going to pass later on the requester pays parameter so that it's then passed on to AWS so that it knows that we're a requester pays. If this was false in this case, we wouldn't be able to access this data. And so what we're going to do is specify that requester pays here. We got a couple other input environmental variables that are set. Again, we got that GDAL variable. And then much the same case, we're reading it in, we're printing off some information about the file. So I'll hit Shift Enter on that, prints off that information about the file, and then I'll print off the Landsat scene for a similar location. All right, so now we've hit 3 different sources, one from AWS Open Data, one from the NASA cloud, and then one from the USGS cloud space. So those are just kind of different varieties of accessing data. When it comes to NASA data, there are slightly different flavors. So we have accessing data that has this an HTTPS URL, as you can see up here. And then there's also accessing data directly in S3, which is something that looks like this with an S3 URL. This is the same asset that was accessed above, but we're accessing it next to the data rather than downloading the data. Actually, we didn't download above, but this accessing data is the kind of the next paradigm that we're trying to encourage, working next to the data rather than pulling the data down and bringing it to your algorithms. So we're going to specify this S3 URL. Again, it's the same asset that we hit above. In this case, we have to hit a service. And this service will return those S3 or AWS access keys so that we then have to pass those to inform the system that we are valid users of this data. And so we'll run that function, which will call a service. Yes.
Oh, just real quick while we're running that. We did have a question in the chat. What does
Yeah, okay.
Yes. Okay.
Sorry. Yeah, so that times the process. So you'll see this printout here, CPU times and wall time. This is the time it takes to run this cell, basically. And it's in there. It's kind of a remnant of, I was doing some comparisons between S3 and HTTPS data access, comparisons against accessing Landsat versus accessing NASA versus accessing open AWS data. Just to get a feel for kind of how fast things are, and if there are any major differences, why were there those differences? And so that's what that percent time does. So you see 10 seconds to access and print out this data. No, that's got to be milliseconds. So that time looks a little off. I'm not sure what's going on there. The wall time, one. Yeah, so that number looks a little off for the R data. So that's what that does. It times the process going on. Okay, so now we're accessing or hitting the service that will give us credentials. We're going to call that service. And what this does is reads that netrc file that we produced earlier. So this will automatically read that netrc file. It will pass it to the service. That service will then give us this access key ID. It'll give us a secrets key ID and this access token. So if you are accessing data directly in S3 or using this S3 URL to access data, this information is required to be passed to the AWS system. So we'll pass that to the session object, and then we'll insert that into our environment here using the AWS session. And again, we're passing this GDAL configuration and some others. And then we will run that cell. theoretically, doing direct S3 access is faster than accessing it through that thin egress app or working with that HTTPS URL. And so this is what we have. We have the same asset as above. So that's data access. Then, I mean, kind of wrapping things up, there's different ways of accessing geospatial data. And it depends on how you're kind of planning on working with this going into the future. If you're very familiar with like NumPy arrays, when you read it in using rastereo, the data that comes back, or is the data model that you're using, it is a NumPy array. There's also a package called RioX array that when you read in a Geotiff object, brings it back as an X array. And if you don't know anything about X array, we have some resources, but I encourage you to go and look at the documentation on X array. It's kind of a blend of pandas, which is kind of a label-based, human-readable way of working with data frames, and then also NumPy. So it's an ND array way of indexing geospatial data, whether it's 2D, whether it's 3, 4-dimensional objects. Very useful, very powerful. A lot to cover there, but we're not going to do that right now. And so this just kind of shows accessing RioX using RioX array. And this gives us kind of a different object back. You can see that it has coordinates associated with it, X, Y. These are in UTM. And then this is a data array. So if I printed out the data, I would have a 2-dimensional array. And I think I'm going to cut it off there because the next part just kind of gets a little confusing. So just be aware, if you're working in Python, if you're using rastereo to access a Geotiff, you get a little bit different data model relative to RioX array, which brings it in as an X array. And then you basically have the entire what's called Pangeo ecosystem available to you. You have DAAC, you have hollow views, plots to be able to explore your data and move kind of further down your analysis pathway. And so I'm going to cut it off for 5 minutes and just see how people feel, open up for questions, and then we can jump into the next one.
Hello, Aaron. This is Yuting.
Hi.
I'm curious about the requester pays session. So you mentioned the AWS account is required for us to doing this, but personally, I don't have an account here. So how was mechanism was handled?
That's a perfect lead into this. So I didn't mention this earlier, but so what you were running in right now is deployed in US West 2. So this is kind of a strategy to give people access to a space to work with these data. So this is a Jupyter hub that's been deployed in US West 2, and who's managing this environment is 2I2C. So this is a group that kind of specializes in deploying environments like this for people to use. And so basically you go to them with money, credits, that says, I want to deploy this Jupyter hub in US West 2, here's what I have. And then they manage and deploy that system. And so each of you are running on an instance within this Jupyter hub, a Jupyter lab instance exactly or precisely. And then you're actually in US West 2 without really knowing it. So all of this action is being done in the cloud, which is why we can access a S3 URL. And it's also, since it's in US West 2, it's free for us to use. And so that's why we can access Landsat data without being charged to the project anyway, not to you all. So yeah, that's what's going on here.
Okay, great. Thank you.
Yeah, and we have some probably oldish now instructions on if you want to set up your own AWS account and deploy a Jupyter hub, or even just like a Jupyter environment. We have some instructions for that if that's something you are interested in. The way I kind of envision kind of things working in the future is that that's all stuff that's handled by an organization. It's kind of my opinion that, I mean, this type of thing, setting up the infrastructure, setting up the environments are not necessarily something that scientists should have to worry about. I am of the belief that you basically give them an environment that's already pre-set up for them, and they let them go, let them work, and perform their science. And so that's kind of the kind of point here, is that give you a space to work from and let you go. Now I'll let Massa or Danielle do a quick lookup on 2I2C and put in a link. Okay, so let's move on to the next exercise then. Cloud optimized data. Hopefully this one will be a quick one. Again, we're in the LPDAC Cloud Data Access folder. We're in this Notebooks folder. We're on topic 2. So this is, again, not necessarily an LPDAC specific exercise. This is just what is a cloud optimized object, specifically what is a cloud optimized Geotiff. And it doesn't really go into detail, but it's kind of a way to explore those, specifically explore the overviews of a file and the internal tiling and what that gives you as a user experience. And so we're going to import a number of packages here again. And so we'll do a shift enter on that. And then we're going to, so in the previous exercise, we were running each cell, we're passing credentials in each cell. There's a way to set it up so that those credentials are used throughout a notebook rather than within a cell, because if you run it only within the cell, those credentials don't get passed on to the next cell that you're running. But you can set it up like this, where those credentials are viewable or usable throughout this entire notebook. And so this is a way of doing that. So we're going to set up that S3 credentials function again. And we're going to call that function again, which is, again, reading our netrc file, bringing in that access key ID, secret access key, and this access token. So we'll, again, assign that to that sessions object. And then we're going to create an environment that's implemented across this notebook. Again, the GDAL configuration, the cookies file, and a couple other ones that are more for efficiency rather than actually being able to access that data. But we're also passing in those AWS credentials from this sessions object. So now we have an environment where we can just basically freely run and access that data. We're going to specify this URL here, this HTTP, and we're just going to do some exploration of this file. We're going to specify that URL, and then we're going to open it, and we're just going to grab the overviews in this case. Take a look at that. So you'll note that we have 4 overviews here in addition to the source resolution, right? So what makes this useful is if you're, I guess, like an application and you're at full extent, right? I mean, the level of detail that HLS has at 30 meters may not be necessary at full spatial resolution or at full extent. And so you would want to use levels to effectively move in and out, or overview levels to move in and out on that, that object and be able to read it effectively. And that's what you can do here. So we're going to plot overview level 1. So we're going to grab that second overview level, right? And you'll notice the source file actually has a YX of 3660 by 3660. And so this overview is a degraded or coarser resolution image, right? That actually is accessed and visualized much quicker than the source file. We'll grab the next overview level, or 2 overview levels up, and this one's even faster. It's even more coarse in its spatial resolution, so 229 by 229. You can definitely see the degradation in the image here. So if you're at something like a full extent image of the United States, I mean, having this at full spatial resolution wouldn't be very useful. But if you want an image to display, using a coarser resolution image is desirable and faster. So that just shows you quickly how to grab overview levels from that cloud optimized Geotiff. Now, overviews aren't necessary to be cloud optimized, quote unquote cloud optimized, but they're very useful and they make them more usable at a kind of an application level. What is mandatory in a cloud optimized object is chunking. And so here we kind of have a visual representation of that, where rather than a file being read row by row by row, it's actually being read by chunks. And the benefit is that if I have this red rectangle and I want to request data for only that space, I would have to read each of these rows until I got to the end of that rectangle, which is much more data than I need to read in. In this case, with cloud optimized objects, I would request this red object, and all that would be returned are these 4 chunks. And so it's a much more streamlined, optimized way of accessing data within a file rather than having to download the entire file. And so this just shows how to do that. We have some kind of vector work here where we have a GeoJSON file that's saved off for North Nebraska to identify some ag fields. And so we're going to run some operations to read that file in here. We'll just kind of print off some information on it too. We're working with the geodata frame. And this hopefully doesn't get too confusing. We're doing some vector analysis here, or actual manipulation to get to a box that we can then clip against. And so we'll read, again, that shapefile. We're grabbing the geometry now. We're identifying the corner coordinates of that object. And we're going to save those bounds off eventually, but first we're going to plot that out. So you'll notice that the GeoJSON file is in geographic. These are decimal degrees. And we have just a simple print off of that file. So we got 4 fields going on here. And so this is an interactive visualization. So if you click this tool here, I can zoom out using my the pin. And so very small relative to what a scene would be, right? So rather than having to read that entire scene in, we want to just read in the minimal amount of information. So what we're going to do is first just show you reading in that full scene. So we're going to open up that full URL from above. We got the projection information. And actually, I skipped a step here. So what we're doing is grabbing the projection information from the source HLS file. And what we need to do is convert the GeoJSON file to UTM units, because right now it's in decimal degrees. And in order to clip something from a HLS or any source raster file, it has to be in a common projection. And that's going to be our UTM projection that our source HLS file is in. So that's what this is doing. This is just translating its decimal degree coordinates to units of meter. So we put that out. Now those units are in meters. So we use these bounds to clip, basically, very simply in the next couple of steps. But first, we're going to read in that entire file. We're going to use this time in this case, right? 62 or 61 milliseconds in this case. Again, the source spatial resolution or dimensions is 3660 by 3660. We have an X-array here that we're working with. So we have our coordinates printed out. We have our attributes that are printed out for us. We can get information about these individual variables by clicking these show and hide. So we have some kind of cat native view of the data values are in the X dimension. We can also get usually some attribute information. So here's some spatial information regarding the projection of our source file. Okay. Then we can print off those spatial attributes again. So in addition to just using this visual up here to investigate that object, we can actually pull that information out using these commands as well. And then we'll do a quick visualization of this. We're using this index 0 because when you read a Geotiff in, it automatically tacks on this band dimension. And so there's a way to get rid of that using a function called squeeze. But right now we're just going to leave it in. We're going to index it by that band. There's only one, or that dimension it has only one. And so that's where this 0 comes from, is we're just specifying that dimension. And then we got a very simple plot of that full scene. Now what we're going to do is use that information from above, the input feature file, and clip this on the way in. So none of this data is being downloaded to my machine. I'm going to clip this on the fly using this Rio clip function, and I'm going to access that URL above. And so that's what we're going to do here. We'll just run that clip. It takes very little time to access that data. Again, same information here. We have a printout of some of the data values, the Y, the X, the band, dimensions, some spatial information. So exactly the same information, except that our dimensions are much smaller. So 56 by 56 versus the 3660 by 3660. So what this did was, identified those tiles that intersect with our area of interest, and it brought it in and clipped to that boundary for us, which makes it much, much faster, much more optimized when working with that data in the cloud. And so doing a quick printout of this, these are just kind of some visualizations. We could see that now we have a scene that's clipped to that boundary. And then we can, I think this overlaps, yep. So we have a scene that has our input boundary that we inserted on top of the base map. You can see that this is how responsive this is going to be. There we go. Just a fraction of the original image. And this just shows that your geotransformation, the information that you need to tie this array somewhere spatially on the globe is passed on and modified when you do that clip. And so you can see that those corner coordinates are modified here. We have the same spatial resolution here. And so that you can write this clipped file out as a Geotiff and have it geo-referenced correctly. And then these next kind of steps, we did kind of an area extraction above. Now you can do actually a point extraction using some Python. So we're going to pass the lat long array here, or the lat long point in this these two arguments. And we got to use a different package to transform these point coordinates to our meters, right? These are in decimal degrees again. So what we'll do is transform those to meters using this next cell. And then we'll do a select of that X array above, and we'll print out that value. And so this is basically saying I have an X and a Y coordinate in UTM. I want to pull out the cell location that intersects with those coordinate points, and I want to use nearest neighbor in case it doesn't intersect exactly with the center of that pixel. And then I want to print out the value. So that prints out the single value. And then this, again, just does some visualizing. So we'll run this. We'll turn it into a data frame that we then turn and plot on a map here. So we have our original boundary with our clipped area from that HLS file and our point location here. So that is the end of that one. Hopefully we have a little bit better feel for cloud optimized objects. Again, cloud optimized geotiffs are not the only format in that class. There are others, and depending on kind of the needs of either the data set or the needs of a scientist, you may find other formats more usable and more manageable, I guess, than maybe a cloud optimized geotiff. So I'll cut it off there again. And probably open it up to since we're at 2 o'clock, are we scheduled to go to 3?
Yes.
Yes, I'll open it up for, do we want to take a little bit longer break, a 10-minute break? I know it's kind of a fire hose, so let's let's take maybe a little bit longer break and come back maybe at 2:20. Well, 2:20 Eastern.
That sounds good. Yes, it's 11:09 here in California, and we are scheduled to go till noon. So,
and I think that should be perfect. The next one should take about 20 minutes apiece, so we should be good. And I got my water here, so I can stay around for questions. So feel free to ping me if you have anything.
Hi, Aaron.
Hi.
Hey, my name is Milagros. I am working at UC Davis right now, and this is all very new for me, and I appreciate the workshop, and everything is working right now, which is great. I am happy for this. So I have a couple of questions. So this is working because you set us to work in there, right?
Yes.
And if I want to work myself with this same resources, I can still do that, or every time I have to request access?
So for this environment here that we're working from, you'll have 2 weeks of access to this environment.
Okay.
And we have to do that because yes, there's a cost associated with using these environments. And so the plan is to kind of give people space to play around with and ask their questions and explore. And then, I mean, like you, which I'm guessing the next question will be like, how do I set up, or how do I get like the instructions, I guess, for setting up, or the packages I need, you know, how do I take this and work with it on my own if this environment is available to me? And so we do have ways of saving off the requirements for this environment. And that's pretty simple if you're just looking. We use Conda in this case. So if you're familiar with Python, there's a
little bit, yeah,
package manager system called Conda that we use. And so very simple. I think actually there's a setup file in the top one. And we have this command in here that downloads basically what you need to run these files. And actually, this probably needs to be updated. And it uses a different flavor of Conda called Mamba, which is a little bit faster. And you'd have to ask a computer scientist why, but it's a compiled version of Conda that just really downloads and sets up your environments faster than using just the straight Conda. But we can save a more extensive list off, right? So if I mean, this environment that we're working off right now is big. And so and the intent of this environment is really to give you everything you need for really any application that you're doing. And so you can see you got a lot of libraries installed here. But maybe if you're working on a project-based way and you have very refined needs for packages that you install, you can handle that a little bit differently. But I mean, what we want to do is create a space works for everyone, hopefully, and just give you the experience. And then afterward, we'll work with you to, I mean, what was your environment like? This is what our environment. Here's the YAML file that you can use to install the same environment. Point you to the resources that we have on the subject. So we have these notebooks that you can access. We have notebooks that show you just accessing the HTTP URLs, because if you're working locally, that's what you're going to access is the HTTP. And if you're in the cloud, you want to consider using the S3 links, even though the HTTP links are still available to you in the cloud. So yeah, so if you're interested in kind of next steps after this, feel free to reach out, and I'll gather the information that we have and point you to resources that we know of that will help you kind of get going. The hope is that, I mean, we'll reach some critical mass with these types of outreach events where scientists go to their organization and say, hey, this was a good experience. I was able to accomplish a lot. Can we set up a Jupyter lab that's in the cloud and make it available to my project? That's kind of the hope. And then there's other kind of opportunities within NASA specifically, where they have this thing called Science Managed Cloud Environment, which I think you can more or less, I mean, approach them and say, we have this amount allocated for funds that we would like to apply to an environment. They would set up the environment for you and be that manager of that deployment. And then you could do your work within a similar notebook, similar setup as you do here.
Thank you, Aaron. Oh, and I had a very quick question also about the images that we were looking at. Is this, what are we actually looking at? Is it the red spectra or, yeah?
Yeah, those, we're reading on band 4, which is red for both Landsat and Sentinel. And we're just applying a red color map to it. Nothing crazy. That's okay. What we're looking at. So if you're looking at, so we're using a package called hvplot to plot those data. So you may be familiar with matplotlib. That's a library that's supports or is underneath hvplot. But what I like about hvplot is it's fairly intuitive on plotting the data. I mean, really, I'm pointing to this data object up here. I'm saying hvplot image. Hey, these are my X, my Y coordinates, specifying a dimension of the output image, and boom, it gives me a very quick interactive map that I can work with. And I like it because it's a good tool for exploratory data analysis, just to see that, I mean, you're in the right location, your image is lined up, because I think it's very useful in my opinion. You can deep dive and apply, where do we got? Like overlay images, you can apply color maps, you can put the base map on, you can reproject it if you want on the fly. So it's a very powerful library, in addition to being able to save off an image. So if you can create publication ready images here with some tinkering, much like you do in, say, ggplot in R. And so very, very useful tool in my opinion. But yeah, we're just reading in the band 4, which is red. We're just applying a red color map to it.
Thanks a lot.
All right, I have 2:20 on my side. So I think I'll start to get this kicked off. They do run a little bit long. Hopefully we can, there's set up to be 20 minutes apiece, but we'll see if I ramble as I have been. So there's different ways of discovering data in general from NASA, right? There's the Earth data search that Danielle showed, which will, I mean, if you get down to or search for the data, you can get down to the HTTPS download links. You can also get the S3 links if you want, so you can grab those as a list. And really, you can grab those and bring them into Python easy enough if you don't want to use like an API to do your searching. There's also the API angle for searching and bringing in data. Well, not bringing in data, but searching for data given certain parameters, right? Bounding box, a time range, maybe cloud cover. Just to kind of depends on your needs. When it comes to NASA data, there's two APIs. There's the CMR API, which is the API on top of the Common Metadata Repository, which really gives you access to every metadata field, most metadata fields that are available to us at the archive. It's very robust, very deep. There's also another stack or API called the CMR Stack API, which is built off of the Spatial Temporal Asset Catalog API, which is a specification that has been kind of developed in the public domain that allows for search on very common geospatial information, things that you would typically use to filter your results, whether it be the bounding box, your point of interest, whether it intersects or if it just is a precise match to your bounding box, your temporal range, the specific collections that you're interested in. It's a little different way of, it's a different API, of course, but it plays with other open source utilities pretty well, such that you can request the information from the API, and then that information can be passed on to another utility within the Open Python environment, and you're kind of off and running with that at that point. Whereas with the CMR API, you'd have to translate it into some other object that would be readable by another utility. So spatial asset catalog, spatial temporal asset catalog is what I mean by stack. Again, it's a specification. And it kind of is made up of 4 loosely coupled specifications. We have the API, of course, which gives us the setup for submitting requests to the system to identify those assets that we're interested in. And then we have these 3 other components called collections, catalogs, and items. Items are kind of the fundamental piece, the geospatial spatial temporal object that we're interested in, kind of maps to what we typically call a granule. It has very common, or it has common, or the files within have common spatial representation, have a temporal representation. All of those filterable fields are common within a single item. We also have a catalog, which is kind of a high-level aggregation of the information contained within that stack, and so it's kind of a way of organizing your stack metadata catalog. And then we have collections, which are the common pieces within all items. Is it a HLS L30 collection? Is it within this tile or within this time frame? So you can kind of organize them differently. But essentially with the CMR Stack API, collections kind of equate to a data product. So HLS S30 is our data product. That is a collection in stack. And then within it are the individual granules or stack items that you can query for. And then a kind of a next level step in the items is, I mean, the items contains metadata, but it also has these things called assets, which are the downloadable assets that you want. And so for HLS, we have multiple Geotiff or COG files that are assets within this item that are downloadable. Also, there's metadata files that you can pull as well. but you're trying to get to that very atomic file that you want to pull in to access. So what we're going to do is read in a few libraries again. Specifically, we're interested in this PyStack client. This is a client for reading stack metadata or stack catalogs. And so we're going to read that, or hit a shift enter on that. And then this is the high level stack API for CMR. And one thing to note, now that that cell is run, is when you're using the CMR stack API, you cannot query all assets underneath NASA's umbrella. You have to kind of pick a path. You got to pick a DAAC basically. So LP Cloud is the LP Cloud assets, PODAC Cloud are the PODAC assets. So each of us have our own path within this API, and you have to kind of choose that path. You have to know the data belongs to a specific DAAC before you can use this stack API effectively. And so what we're going to do here is print off all the catalogs within our NASA catalog. And so we do this using this, access that catalog. We'll grab the title of each of the providers is what they call it. LP Cloud is a provider. And this one takes a little bit of time, but so here we have about 52 providers. And this lists out all providers. So the on-prem and the cloud providers, in this case, LP DAAC ECS is our on-prem archive versus our LP Cloud, which is our cloud archive. So what we're going to do here is create a new catalog that appends LP Cloud to that original API, stack API endpoint. And so this now connects to the LP Cloud stack catalog. So now we'll print out that catalog off a bit. So what that you're seeing here is this is a stack catalog, right, for the LP Cloud. And these are all the relative links. And this could be, it gets a little messy, but this has a direction to all the collections that are available. This points to the search API portion of that. But we got a question coming in. Can researchers use Stack to publish metadata from raster data? Yes. Yep. So Stack is very flexible in that, I mean, basically, if you have anything that's accessible over the internet, you can make that a relative link within the asset. We'll get down to that, I think, later on. And so these are collections here. So this kind of takes the extra step for you and takes you all the way to a single collection. But these are all kind of links that have been assigned to this catalog. So we'll do grab the products here. So what this is doing is going into this collections endpoint and then grabbing these individual collections, the Aster GDAM, HLS, L30, and S30. We'll print those off here, and you'll see that, of course, we only have 3 collections in the cloud right now that are publicly available at this time. And so if we look into one of these collections, so if we hit products, and we specify the second object here, L30, and print it off as a Python dictionary. All of this is JSON based. So we have a very object to dictionary workflow that works well in Python. We'll see that this collection is HLS L30, the version of Stack here. We have the description of this collection in this, and then all of the kind of links that are related to this specific collection. So there could be a metadata file in here. There is this is technically a metadata file here. This is a Stack metadata file. All these other are kind of, these dates are used for internally at ISDIS. But now we want to get into the individual items. And so we're going to really drill down into the the granules that we want to access. And so we're going to use the start using the search API here. Kind of blowing through some of this. We're going to, again, read in that GeoJSON file for the Nebraska egg fields. And what's going to be different here is that we don't need to transform the coordinates to some source projection. In this case, the Stack API accepts geographic coordinates. And so that's what you use to make your intersections spatially in here. And so real quick, we're going to read in that JSON file again, get the geometry information, and we'll do another quick printout of that. Same thing, same story here. And then we're going to load that in, that JSON object that we have here, or that object here, into a JSON object that contains those boundaries. So we're going to assign that to an ROI because we're going to pass that to our search function later on. So now that we have our boundaries that we'll be searching on, we want to specify a date range. And so there's multiple ways of doing this. You can do a closed interval down to the second if you wanted to. You can do an open interval if you wanted to. This is theoretically possible with the Stack API in general. The spec allows it, but for some reason I haven't been able to get it to work with the NASA Stack API. So if you're trying that, don't expect a success necessarily there. But it's something that's kind of interesting, at least to me, is that you don't even have to specify down to the second all the time. I can specify a month, and this will return everything that's in May, June, July, and August in this case. Or I could specify 2021 through 2022, and get everything that's within that time frame. And so that's, I think, pretty powerful. And so I like specify for those 4 months here. And then I'm going to specify my collections argument. And so I'm going to run that. And the way you get this here, these string characters, is when we print off the collections above. So that information that we have assigned there are the IDs, these PIDs here, that you would use to insert into your collections. So that's what we do there, is just put in both. In this case, we're using Harmonized Landsat Sentinel. It's designed to be used together, even though it is two separate products. We're going to bring them together and use it as one time series stack. So now we have our collections, we have our date range assigned, we have our area of interest, or ROI. We're going to specify those in our search argument here using those parameters in here. And so these collections, intersection, and date time limit, those are all parameters that are laid out in the API documentation or the spec. And so we just assign the variables here, the collections that we specified up here, the ROI that we specified above, and also the date range. And then we're going to add this limit. By default, the CMR API and the CMR Stack API only return 10 items, even though it will hit, quote unquote, hit or match as many items as are available in the record. But what's returned to you in Python is only 10 items, technically. So you got to use paging to go over them, or you can increase the limit here to match what you request. So we'll kind of see where we land here. We have a match of, I guess, a 113. Yes. So we have 113. So if I had this set to 10, or if I left it at default, and I started to do more processing with this search object, I would have only had 10 records to work from, and then I would have to use a paging capability to go to the next record to process those. But I just bring it in all as one object because it's not too many at this point, and JSON is pretty light. And so we have 113 records that meet these search criteria that we specified. And now we'll grab the information that is in this search object, and we'll do get all items. We're grabbing all of the items that were returned. Those are stack items, and so we'll take a look at a few of those. And so this is the object that's returned in Python. And when I say PyStack client is part of kind of an ecosystem, or Stack is part of an ecosystem of kind of loosely connected packages that are being developed and co-developed within the ecosystem. Like, you could pass on this list of item IDs in this current form, and something like Stack, which is an open library, would be able to read this collection list and read it in as one giant stack at some point anyway. Right now, there's some bugs in it, but so that's what I mean is these loosely connected packages can communicate with each other, and so very easily you can create, if you're familiar with appears like what NASA talked about early on this week. You can really make a kind of Python-based personal appears system that makes extractions for you. And so then we'll kind of grab one of these items, this first one, using that 0 index, and we're going to print it out as a dictionary. So let's do that. So now we have this item, which contains our metadata information. We got an ID here. This is the granule ID. We have some properties, the date, time, cloud cover in this case, 36. We got our geometry. And then we have these things called links, these relative links, and assets. And so getting back to the question asked about saving metadata, I mean, you could definitely save a metadata file in here because we already do. We have an XML file that's a metadata file that's referenced here. And so you could definitely, fill it in with metadata if you want. You'll notice that there's multiple TIFF files. These are all the bands that are available for HLS. And so that's just the object that we have now. And now we're going to do some Python processing to filter this down a little bit more. What we want to do is identify items that are 25% or less cloud cover. And we want to create say our use case is create an EDI calculation and build a time series stack out of that and use quality to filter out our good filter for bad quality pixels. We're going to create a list that filters that object above and just returns these 4 bands. And you'll notice that these aren't one-to-one between the L30 and the S30. The band names are not consistent all the way within these two products. B05 is near infrared in Landsat. B8A is the same spectral range in Sentinel. And so that's what you're seeing here. They have the same spectral range, they're just named differently, and we'll save those off and combine them later on. And so we're going to run this kind of block of code here that's going to do the filtering for cloud. It's going to filter for our Sentinel bands. It's going to filter for our Landsat bands, and it's going to add it to a list here. Add those URLs to a list. So we're going to run that. I didn't run these 2 above, so I'm going to run the cloud cover again for the first time. Run my L30, S30 bands, and then I'm going to run that block pretty quick. And we can print off the first 10 here. You'll notice. Sorry, you see a big screen shift here. Okay. So these are the URLs that are extracted from that stack item above, that list of stack items, and this has all the URLs for our bands that we're interested in, B4, 5, 8A, and FMAS. Okay. What these next parts do are split those bands up. First by tile, right? So when we made our request, we did not make it along within a single tile. It actually intersected with 2 tiles, T14 and T13. And so what we're going to do is create a list of just tiles that are in 14 and files that are in 13. And then we're also going to take another step and break that up by individual bands. So we're going to save off lists that are band 4 specific for tile 13 and band 4 specific for tile 14, right? Is kind of the idea. And that's just really kind of using some Python wizardry at this point. And so that's what these next lines do. We're going to first create an object that we save those tile breakups to. And so this will split up that this list here that we got by tile, T13, T14, and it will assign them to a key value pair. So one value to many, one key to many values is what's going to go on here. And so you'll see here that we have two keys, T13, T14, and then within that T13 key, we have all the bands that are associated with that, that specific tile. And then we're going to take the next step to split it up by individual bands. So we just have a time series of band 4 saved as a list. So we'll run this one, and that solidifies the above. Click off the above again, basically. And now we're going to break it up by band. So we're on this split links by band section. Again, we're going to create an object that is going to be able to accept the breakups or create those key value pairs. And this line just says basically split the URL and identify the band and assign it to its own list. We have, again, a dictionary that has keys of B04, B5, FMask, and so on and so forth. And then within that B4 dictionary object is all the B4s in time, basically for the single tile. All right. So this is just one solution to a problem, and my intent here was to, really keep it within tile. I don't want any mosaicing going over a tile, not having to deal with mosaicing across tiles at this time. And I just want to build a simple time stack for a single band. And then later on, I can use more Python magic to bring those together into a data array that I can then say calculate EVI and apply a mask to that file. So this final step basically just writes off this list up here. So what we generated here is going to be written off as a text file here. So if we run that, we'll have a text file that gets generated. If you go back from notebooks and you go into data, you'll notice that there's a number of text files that were generated here. And those are each specific to their band, so B2. Okay. Going through that pretty quickly, sorry. And then we have a line here that it's the stack metadata doesn't return the S3 URLs, but there's a trick to substitute the S3 portion with the domain that we have for the HTTPS link. And so it's just a straight URL switch or string switch, and that's what we do here. And now we have the S3 URLs in the text form. So here we have S3, and this will access an S3 object directly. So that's the end of that one. Again, a lot of information. Encourage you to look up Stack itself. The CMR Stack API is pretty powerful, but I mean, in my opinion, Stack is a very powerful piece of technology that really is going to allow us to do truly cross-archive type data extractions or data discovery to bring them in, especially if they're in the cloud or those archives are in the cloud. So some reference down there, and then jump on to the next one. I'll give a few minutes for questions and a break if we're up for it. We're going to be fairly tight for time, but I think we'll make it. And I can stick around if the Zoom stays open afterward if you guys have any questions, guys or gals, sorry. And we can just kind of get right into it so we can stay on time. This next section is called analysis in place or data proximate compute, which is more or less a way of saying, rather than taking or bringing data to my algorithm on my local machine, it's about taking your algorithm to the cloud to execute next to the data. And that's what we're showing in this demonstration. I'm going to read in the packages like usual. Again, we're going to set up that kind of notebook environment where I don't need to constantly submit my credentials. It's just applied throughout the notebook. And so these next 4 cells are what do that. So we're going to get our S3 credentials. We're going to assign those to an object. We're going to assign those again to a session here so that they get passed to our work environments, and then setting up that environment. So real quick, we've done this before. Again, we're just accessing that S3 credential service, or assigning what we get back to a object that says, hey, I'm a valid user of this data. So we'll read in, list out those files that we printed out earlier. So here we got all those text files. Okay, and now we're going to read in one of those files, the T13 B04 links for S3. So here we have the list out of that file. So this is just a very straightforward text read. And now we have an object with a list of all those file links. And then we'll do the same for the near infrared, but remember that the near infrared for Landsat and Sentinel were not consistent. So we're actually reading those files in, combining them, and then saving them to a near infrared S3 links object. So that's what we're doing here, reading in both text files and then saving it to that object. Okay, and then we'll do it for FMask as well. So we read in the near infrared, we read in the red, and the FMask for quality, and I'm guessing you're guessing that we're going to make an NDVI layer, which is what we'll do later on. I thought we read in, okay, we did, and then we did that, right? 9. Sorry for all the movement, I got lost in that. Okay, so now we have a list of the URLs, the S3 URLs for FMask, near infrared and red. Now there's multiple ways of doing this. This is just one example of creating a stacked time series. There's other examples of doing it within a loop within Python. In this case, we're going to use GDAL, and we're going to use GDAL VRT specifically to create a time series stack VRT file, and we'll save that off, and then we'll read that into Python to create an X array. And so we're setting that up here. And let me see what this exactly does. Oh, bugger. Got ahead of myself again. So another kind of note here. So if you're using Xarray or RioXarray or Rasterio, these are utilities within Python. They have the understanding, the knowledge to do this thing called leverage the virtual file system capabilities of GDAL. If you don't use those, you actually have to manually specify or swap out the URL so that GDAL knows, or the utility knows, that this is an S3 object that I'm reading from a bucket, or if it's a HTTPS GET request for the data. It's a manual process that you have to do when you're working with GDAL directly, which is what we're kind of doing here. And so we're modifying, in this case, this list of URLs and swapping out the S3 for VSI S3, which tells GDAL that this is an S3 link that I'm going to access in the cloud. And so that's what these three steps do, is just modify that link. Again, I'm going to read in that boundary file. We're going to blow through that. to get that information. And we're going to have to, again, do that transformation here. So I just shift entered on all three of those. And what we did, again, is transform that input ag field from geographic coordinates to UTM meters in this case. So what we're going to do now is set up our build VRT command. And this is kind of a manual process. So if you're familiar with working with GDAL from the command line, that's what we're doing. We're setting up a command line executable or a call. And then we're going to pass it to this thing called subprocesses.call, which is just Python executing a command line command from Python, and then creating that VRT file. So we'll create a red VRT file, and then we will execute the subprocesses call, which has taken a much longer time than I expected. So not sure what went on there, but we got a success if it's a 0. We're going to do the same for the near infrared. We'll do the same for the FMASC process. So this is creating a static file on my system, but VRT files don't have data. They have metadata. They point to the resource rather than downloading the data. So this has a stack of reference information to the input URLs that we mentioned above. And so now I can use RealXArray here to read in those stacks as a XArray. So now that's what we're going to do. We're going to read in the VRT file. So this just read in a 32 time stack. Well, it just read in 32 bands or time steps at full resolution here. And again, actually, I mean, what's happening here is XArray is not actually reading the data in, it's reading metadata at this point. So there's technically no data arrays stored in memory right now. It's just basically reference information to the data and metadata. And so again, we can print out some abbreviated views of the metadata and reference information. But if I try to print out the data values for this array, it'd give me a different view of the data. Let's see if we can do that. We'll do it. Enter. What do you call this? Red. If I call it values, it will print off the data values. Or data. On the spot. So if I print off data, if this was in memory, if this data stack was in memory, all the data values would have printed off in a concatenated view anyway. But in this case, it just gives me a kind of a representation of the data it's representing in here. So the 32 time stack at full resolution. That object, we can grab the time information. So this is all the times within this time series, which we can use then to kind of interrogate or narrow in on specific locations if we're plotting or if we want to grab the data. The GeoJSON file, we can read that in now, and I'm using this persist command in this case, which is now actually reading the data in, because the idea is, okay, I don't want to work with the full spatial resolution data because it's a lot. What I want to do is build a recipe that says, okay, I'm going to read the data, I'm going to clip the data, I'm going to calculate this indices, and then I want to load the data at that point. And so that's what we're doing. It's just kind of creating a recipe, and then when you want to load that data, you use something like .loads or .persist. And so that's what we have here is that data is loaded into my environment. And again, we have the 32 time steps, but we have a much smaller spatial area that we're covering. And then we can do a plot. So if this was not in memory, this would take a little bit of time. And so since it rendered so quickly. Now I have a time series plot. So we're, again, using HV plot image. And we're specifying some parameters here. We got that color ramp red again going. But we now have the ability to move through the time series and visualize that real quick. We noticed that there's a lot of cloud contamination in some of those earlier ones. And actually, there's a ton of cloud contamination across all these images when we do our filter. So a quick visualization there, very simple. And then again, we're going to do the same for the near infrared. We'll do the same for the F mask. Responsiveness is so low for some reason. And then what we're going to do now is create a new data set with red, near infrared, F mask, and we're going to create an NDVI layer on the fly. Okay, so something you see now is this, again, is not in memory. This is an object that refers to our red data set, which refers back to the actual URLs. In our near infrared, our F mask, and then this would be calculated on the fly if I were to call it. And so this is really just a reference object. Nothing's read into memory yet. Full spatial resolution, we have the 32 time steps, and now you see that we have 4 data variables: red, near infrared, F mask, and NDVI. So now we can execute that clip against this object, and we can then request that data to persist in memory. So now that's what we're going to do. I shift enter. So this is, again, creating a recipe. Now it's going to go through that recipe, create that NDVI, and then clip it, and it's going to save it to memory. And these are all kind of warnings about some actions going on in the data. They're not deadly to the functioning of it. And so now we have, again, dimensions 56 by 56, 32 time steps. And again, we can do the plot. Should happen pretty quickly since it's in memory. And now we have an NDVI plot here. So time series, again, has all the contamination that we saw earlier with the F mask, or the red band. Okay. This is 32 time steps that we have here, going through them pretty quickly. Here's just a pretty straightforward quality filter. The best quality that you can get with HLS is a data value equal to 0. Unfortunately, if you do that for this data, you'll get no data returns back. So we had to identify a different value to filter on. 64 is kind of the next step up, I think, from 0, where it has some cloud shadow, but it has, for the most part, valid data. And so we do a filter here. Again, doing really kind of everything at once in this one. We're reading it or connecting to that NDVI layer, which was not in memory. We're doing a where statement where we're grabbing only those data values that intersect with F mask and have a value of 64, and then clipping to our area of interest. So this is all one single line of code. We'll put that filter. Again, same dimensions that we mentioned above, and then here's our filtered image printed out. These are the data values that meet our criteria from above. And then something to cap things off. So once it's in this X-array data model, this data is in an X-array data model at this point. You have a ton of advanced kind of calculations, algebra that you can run against that, the variables within it. One is this group by function, where I'm saying, take my NDVI clip filter, group by time, specifically month. So it will identify from our time list the months that those are in, and do an aggregate, a mean, by that time. And so now we're basically creating monthly averages within that data set. So we have month 5, month 6, month 7, month 8, averaged in time. that's just kind of the, I don't want to say icing on the cake, but it's the final message I have. And so that's all I have for you today. And so hopefully that's helpful. I want to say that it's a ton of information. So if you didn't follow along the entire thing, that's perfectly fine. Please, if you're interested, reach out. We are here to help you. We're here to pass along whatever knowledge we have as far as data access and data workflows go, whether it's on-prem or in the cloud. And we have more resources, and feel free to reach out. And if you're interested in additional resources, if you're interested in this work environment, please reach out. We can make those connections for you. So I guess with that, I'll kind of end this talk and open it up for questions if people can stick around.
Great. Thank you so much. And before everyone does leave, I'm going to send out an evaluation in just a moment. If you could please fill that out, we'd very much appreciate it. It goes towards not just our program reporting, but also to help us refine and improve our workshops going into the future. But again, yeah, thank you all for attending, and thanks to everyone from LP DAAC for putting on such a great workshop.
If you want to reach out to us in general, contact information was posted above. My email is
Aaron, would you like me to CC you in the evaluation email?
Totally, yeah.
So it's visible to everyone?
Absolutely,
Will do.
Yep. Yeah, I mean, feel free to reach out again. We're a resource and use us. That's what we're here for. And we just kind of want to get that message out, whether you're doing cloud research, or research in the cloud, whether you have interest in using it in QGIS or ArcGIS, I mean, we'll work with you. So yeah, I just want to say thank you to all of you for coming, and you, Fang, and Sean for setting this up. Awesome. We love these things. These are fun to do, I think.
Thank you so much, Aaron, Daniel, and Masa.
If anyone's interested, please check out the IGIS website for upcoming trainings. We actually have one in about an hour on story maps that I'll be putting on. There's a lot of online resources now available for learning all these various geospatial technology interests. I wish it was this easy when I was first starting.
Well, we're getting to where we're putting out resources at a pretty consistent clip. So now it's like, where's the overlap?
Right.
How do we identify the critical components, which is something we're trying to work with, like where are the areas of overlap that we want to try to avoid confusion. And yeah, so we have an effort with this group called OpenScapes, where we're kind of thinking about that, identifying like the fundamental pieces that we need that you can just take and say plug into your resource or your tutorial or your workflow with a small tinker with, say, a data product name or something like that. So, and hopefully it works as is. And I think we're getting close with that resource.
Yes, there's definitely overlaps, but I also find there's a lot of complementary kind of ways of presenting, ways about how you go approach this with just different, just little different twists.
Yeah.
Very complementary.
Yeah, that was like we have cloud optimized geotiffs in the cloud right now. And it's really kind of low hanging fruit, right? I mean, geotiffs in general are pretty easy geospatial formats. Cloud optimized is no different. And so like we produced our materials and we're like, oh, it's working. This is awesome. And then somebody came in and was like, well, we have netcdf files. Does your workflow work for that? And I'm like, oh, let's check it out. And so we basically switched out the file name and Turns out, no, it doesn't work out very well. So it's like, okay, there's situations where best practices for COGS may not work for NetCDF. So what's the best practice for NetCDF? Well, there's different flavors of NetCDF and how you organize those too. So it's like, how do you kind of adjust for those? And I think I think there's some interesting use cases, examples that I've been putting together for different DAAC data and for sea surface height and for some iMerge data. And there's some interesting ways of working with it, and definitely can get it into the cloud and work with it in an optimal way. So that's always nice to see.
Awesome.
Well, thanks again.
Thank you, and we'll be in touch.
Yeah.
Thank you.
Thanks. Bye.